Okay, so everybody can hear me and everybody can see the screen. Private chat started. So you guys are becoming more sophisticated than I am. I don't even know what a private chat is. Okay, are there any questions? My agenda, I guess, for the remaining 3 lectures would be to introduce this idea of a finite element method, building on the method of weighted residuals, and then in the next class maybe talk about finite volume method. So I'm really compressing these lectures into each topic into one lecture. There are whole books that are devoted to each one of these topics. But at least we want to know what are the differences between various methods of discretization conceptually. Okay. And the last lecture, I will just use it as a general lecture to talk about errors in numerical methods versus errors in modeling and how computers have come to dominate, my philosophical take on that. But if there is anything else that you would like me to kind of talk about, let me know. And the last lecture is going to be kind of open-ended. I'm not having anything very specific. Today it's finite element, introduction to finite elements. You should get the basic idea. We'll use an example to see how the finite element formulation works. What is the difference between the method of weighted residual? It is a subset of the method of weighted residuals. Then finite volume. We'll see notions or concepts of what are conservative forms, what is a weak form. These are terminologies that you will come across when you're reading, for example, COMSOL manual. So what is a weak form? So we should get some idea of what they are. Okay. The book by Finlayson, Nonlinear Analysis in Chemical Engineering. There is an earlier book by him. I think the title is Method of Weighted Residuals. It came probably in the 70s or 80s. They are both excellent books for this topic on method of weighted residuals. And he has contributed a lot to its development and published a lot using this method, a number of problems in chemical engineering. So in the last lecture, we saw what is the definition or a concept of an orthogonal function. Again, these are the things that you should be able to engage in describing to me what you understand. Okay, so don't be terrified of the oral exam. I'm going to spend only half the time, maybe 10-15 minutes on these kinds of concepts, and then the remaining time on your project based on your presentation. Okay, so you should be able to feel absolutely comfortable in your project because you know more about it than I do, certainly. Mrinal probably knows more about it than I do because he has worked with you much more closely. And he showed me yesterday a table of how everybody is progressing. And it looks really impressive. A number of people have actually done to the stage of matching and now getting to the stage of parametric studies. Okay. So I would say put emphasis on your presentation, on your report. They're going to carry significant weight, 25% each. I think the final exam, I'm just saying, is 25% weight. And of that, half of it is going to be on your project again. Okay, so the project is the best learning mechanism. And this is just to see that you attended the course and you got something out of it. Okay, and I want to see how much you got out of it. So don't be terrified of that because nervousness is not good in an oral exam. So we also revisited the concept of a linear independence. We have seen these in vector spaces. So we looked at function spaces and what is the idea of a linear independence. Basic idea is if you cannot express, if I give you a set of functions, if you cannot express any one of them as a linear combination of other functions, then they are linearly independent. There is a test for that. That's a Wronskian. You construct the Wronskian matrix, which is basically all the given set of functions and its derivatives going all the way to the n-1 derivative. You form a determinant, and if the determinant is non-zero, then you have a linear independence. And we revisited the Gram-Schmidt procedure. So that addressed the question, after seeing what is an orthogonal function and how do we test for linear independence, We said, okay, if you give me a linearly independent set of functions that are not orthogonal, how do I orthogonalize them? And that's a Gram-Schmidt procedure. Okay, and we saw why it is important to have an orthogonal set of functions. Can you kind of articulate what that is? Why is it important to have an orthogonal set of functions? Isn't it important? What does it do?
It's mostly convenient. It's mostly convenient. I mean, it makes computations easy because certain things go away from the problem.
What goes away?
The end product.
Okay, can anyone be a bit more specific? Those are very generic terms in the right direction, but I want to get a particular.
You have to solve for the IJ.
That is the key word, diagonalizing. Okay, so it's equivalent to diagonalizing a given matrix in the vector space. If you're given a matrix, you find its eigenvectors and pre-multiply and post-multiply by the eigenvector transpose of it, you diagonalize that. So you decouple the variables. Okay. So another way of saying that is the modes are decoupled. Each eigenmode does not influence the other. So you have an uncoupled set of equations. So it is easy to find the coefficients, which is what I think you were trying to hint at, that when I'm solving for coefficient 1, I don't need to know what coefficient 4 is in the test functions that I have because they are uncoupled, right? So when I take the inner product, I suppress all the coefficients except 1. So I select one at a time and I'm able to solve for it. So if I'm expressing an arbitrary vector as a linear combination of orthogonal vectors, I can find out those coefficients very easily without assembling a matrix that I need to invert. If they are not orthogonal, which we have also seen, a curve fitting exercise. Take a simple curve fitting exercise. You need to assemble a matrix A and you need to invert that, right? And so when you have an orthogonal set of bases, you do away with that problem. But it is not always possible to have an orthogonal basis as the choice. In fact, you forego that when you go into the finite element method. But the more properties that your basis set has, the easier it is to solve the problem, which is what we generically said, which is right. Okay. One of the things in fluid mechanics, for example, is you have the Navier-Stokes and you have the continuity. Okay. So you have to propose a test function for P and a test function for V. If you can propose a test function for V that automatically is divergent free, that's a keyword that they use. That means the functions that you're putting into your test functions automatically satisfy del dot V equal to 0. Then you don't have to solve that equation. You have to worry about only solving the Navier-Stokes equation in an approximate way. So the people have worked on coming up with basis functions for finite element method that contain divergent free thing as an element as a property. So orthogonality is another nice property to have. But if you don't have, we can still work with it, construct the matrix, invert the matrix, etc. Okay? So the basic idea of, let me try again. I think this writing on the board works for a while and then the system gets overloaded, I think. So the basic idea of the finite element method is given a differential equation, L is a differential operator, and some boundary condition lambda on the domain. So the domain is omega and the boundary of the domain is delta omega. So that is a problem. And we want to find an approximate solution to that equation. And so we propose a solution to be something like this. So we split it into two parts if possible, and that is V0 must satisfy the condition on the boundary, that is this part of it. Okay. V0 must satisfy that. And so phi, the test functions that we are proposing, must satisfy the homogeneous boundary condition, if you like. Okay. And we take that function v and plug it into here, and you get a residual. That is your residual. So wherever v appears in that equation, u appears. U is the exact solution to that differential equation. V is an approximation. So when I substitute v in here, it's not going to be equal to 0. Okay? And so that's what we call the residual. And the weighted residual is formed as an integral of the residual, weighted with some weighting function, integrated over the domain. And it is that we want to satisfy to be equal to 0 as much as possible. So one of the things that I probably made a mistake in the last class is I called that as R. I should call it as I, or an objective function, and trying to minimize that objective function. Not exactly equal to 0, but it's my goal to make that weighted average to be equal to 0. Okay? So we saw a series of global methods, okay? And that means that the test functions that I'm considering here span the entire domain X, going from 0 to 1 or A to B, whatever the domain is. I have taken this material, again, acknowledgement. In all my moves over the last several days, I lost all the notes on finite element and finite difference method. So I'm going into the internet and digging up, and there are lots of material. Various math department, they put their entire notes on the net. So I'm just cutting and pasting a lot of these things, as you will see. Okay. So I've taken one example. It's essentially the same example, going through very quickly a review of the method of weighted residuals before we link it up to the finite element method. So you see the difference between, because it falls in the same category, method of weighted residuals, but the main difference is this function phi j that we propose in the method of weighted residuals have a global support over the entire domain. The function is assumed to be valid over the entire domain. And this particular guy has a very nice example that shows what happens if you expand the domain. Okay. So we applied this to this problem, and I'm going to do that again today. Okay. And from an oral exam point of view, we should be able to describe what these methods are, what choices you make, and again, in this box, very simple kind of thing that I reviewed, you should be able to engage in that kind of a discussion. That's all. Because I've heard this feedback, and I want to assure you that don't panic, don't study a little bit before the exam, okay, just like any other exam, but don't panic. Okay, so he had a nice bullet points for showing the difference between finite difference method and finite element method, and I thought it was important to include that. Okay, so in finite difference method, we use Taylor series expansion or Newton polynomials to develop a table of finite difference approximations for various derivatives. But they're all based on assuming that the step size is constant, so that you can use the same templated equation over the entire domain. So you take the domain, divide it into uniformly spaced data, and use the discretization to convert a differential equation into an algebraic equation. Okay? So there is a way to overcome that. That is through the algebraic grid mapping. Okay? We saw one example of that, which basically you still have a uniformly spaced grid point in what we call a computational domain, but there is a physical domain which has non-uniform grid. So you'll have two situations like this. So if this is your physical domain that goes from A to B, we create a computational domain that also goes from A to B. Okay, this is the physical domain, and this is the computational domain. In the computational domain, I put equally spaced data points. But in the physical domain, I might have something like this. I can space them in both points, crowd them, or how do I achieve that? I achieve that by making a transformation. If this is the original coordinate system X, I create a new coordinate eta. Okay? So there is a relationship between X and eta. I come up with that relationship. And once I have that, I can use chain rule to transform every variable from wherever I have d dx. I can approximate that by d, not approximate, equated by d eta times d eta dx. Since I know this function, I can calculate what d eta dx is. Okay, so I can transform the equation in terms of the new variable d eta, and in the eta space, everything is uniformly spaced. I can replace all the different derivatives with difference approximations. But what I'm really doing is clustering the points in the original physical space, where I know the points are, where there are sharp gradients, for example. Okay, so even though this is in general true, there are ways of overcoming that. But the more challenging problem is if I have a domain that is not rectangle or a cylinder, then even if I do this transformation, it would be a bit challenge to make my uniformly spread grid points on the transform domain to fit in that. People have also come up with solutions for that. Okay, and that is what is called boundary fitted coordinate. So if you have an arbitrary geometry, then you will build a coordinate system that kind of fits with the boundary. And will they be orthogonal? What does orthogonal coordinate system mean? From transport phenomena we saw curvilinear coordinates. On every point of intersection, the two vectors that are intersecting are perpendicular to each other. Okay, but it need not be. But if you want to make it orthogonal, you can also achieve that. And there is a paper by Leal and Ryskin, I think, that address this problem of how to construct orthogonal grids for problems that have complicated shapes. One of the problems that they were looking at is flow through a sinusoidally varying cross section of the pipe. Okay, this was supposed to be a model for flow through porous media, and if you have a droplet that is moving through that, what does the droplet do? As it goes through it, it deforms, and then when it comes back, maybe it breaks it into two or whatever, right? So how do you fit a boundary fitted coordinate system for such a geometry? Because there are no natural coordinate systems that would fit with that one. So you can generate that idea computationally, extending this notion of what we can do analytically for this, we can do it numerically by solving a Laplace equation in 2 dimensions and mapping the physical geometry into a computational geometry that looks uniform in space. Okay? So wherever we have a problem, we think about it and we come up with a solution. Okay? Of course, the rest are all fairly straightforward. At each node, we replace the derivative, and we end up with a system of algebraic equations. That is always the goal. Whatever the method is, finite difference, finite element, finite volume, whatever it is, differential equations we cannot solve, clearly not linear ones. We reduce them to a set of algebraic equations, nonlinear, which we know how to solve. That's why the Newton method, continuation methods, they are all applicable for all these problems. Okay. Any questions? So they point out why finite element method, and it utilizes uniformly or non-uniformly spaced data, because if you have a complex geometry, you can put a structured or unstructured mesh in that, and how do we do that is what we're going to talk about today. So within each element, the change of the independent variable is approximated by an interpolation formula, or construct a basis function in each element. Okay. Once again, the original problem is replaced through a process of integral expression. Well, that's what we did with method of weighted residuals. What did we do with method of weighted residuals? We proposed a test function. We formulated the residual as an integral, and we minimized that integral. Okay, we minimize the error in an average sense over the entire domain. So we convert the differential equation into an equivalent integral formulation. And there are subtle variations on that, and this particular lecture notes covers that very well. Okay. It's really going to take us more time to really fully understand, and I'll give you references for those who are curious to read more about it, but I just want to go through the basic ideas very quickly. Okay. So the interpolation functions, basis functions, test functions, whatever you call them, we put them into the integral equation, and the basis functions can be integrated and eventually converted into a set of algebraic equations. That's the goal. Because again, we're going to end up with a set of algebraic equations that we can solve. We're now talking about equilibrium problems. Okay. So if it is a dynamical problem, then you'll convert that into a set of ordinary differential equations in time. Okay. Same idea that we use for method of lines, for example. And then the time discretization has to be taken care of explicitly. So we are really talking about spatial discretizations in all these. Okay. Let me just check if there are any issues there online. Okay. So it's the same example that we saw in the last class. Okay. That is du dt equals lambda u. Okay. This is just an ordinary differential equation, a first order ordinary differential equation. And our interval, we are confining it to 0 to 1. Does it make it a boundary value problem? What kind of a problem is it? Is it an initial value problem or a boundary value problem? when you are given that u at t equal to 0 is 1. It's a first order equation. You can take only one condition, right? So it is an evolving problem. It's an initial value problem. T, you think of it as time, but he has focused the attention only to the interval 0 to 1. Okay, and let lambda be equal to 1 to simplify it. Okay, so you know the solution to this problem, analytical solution. So we can learn from comparing with whatever we are getting numerically. And that analytical solution is simply it is e to the power minus t. Okay, and you can expand that in series, and it's an infinite series in the independent variable t in this particular case. Okay, now we are saying, okay, I'm going to construct an approximation to that. Suppose, assuming that I didn't know that, if I have to solve this equation, how can I solve it numerically using method of weighted residuals? Okay, so we're going to propose, so u bar is an approximate solution. U here is an exact solution. Okay, so u bar of t is given as a0 plus a1t plus a2t squared. So what is my basis set here? 1t t squared t cubed. They are not orthogonal. Okay, so the matrix that I'm going to end up will be full in this particular case. Okay, so I need to find out the best value of a0, a1, a2, etc. that approximates the solution to that differential equation. I can then compare it against the exact solution that I have here. Okay, that's the goal. Now, I said we will split this into two parts. Okay, the first part that satisfies the given condition, and the next part that's going to approximately satisfy the differential equation. So in order to do that, I know that in this case it's 1. Sorry, the initial condition is 1. So I pick a0, my first coefficient to be 1. So it's easy to satisfy. When t equal to 0, all these terms drop out, and I get my condition satisfied, the initial condition satisfied. Okay? The solution for this is going to be something like this. This is t, but it's going to go from 1 to whatever, to infinity. That solution is an exact solution for all values of the independent variable. Okay? But I'm going to apply it only over this interval, 0 to 1. Meaning I'm going to require the residual to be as small as possible only over that interval. Okay, I'm going to minimize it over that interval. And then ask the question, does that solution that I have constructed by minimizing this over this interval remain valid beyond that? What do you think would happen? You want to take a guess? Most of you are shaking your head like that, and that is the right answer. It won't be. You are minimizing the error from 0 to 1. It will be a good approximation over that interval. But if you plot the result for outside, it's going to go something like this, the approximate solution. Okay, so it will not agree. Then you can ask the question, okay, well, can I make it better over a larger range? What would you do? Increase your range over which you are minimizing the interval to 0 to 2, okay? Or 0 to 3, or whatever range that you want. That's the basic idea, okay? And leading up to that, you have the residual that you are forming here. And he's taking only, we're interested only in the interval 0 to 1. And I'm going to take only a second degree polynomial. He says that somewhere. Where does he say that? Anyway, that's what he does. Okay, I thought I saw it.
Quadratic, third line.
Third line, class quadratic, yeah. Okay. Even though he's written it up to n, truncating it to a quadratic function, a global solution, global in the interval 0 to 1. Okay. And so so you take that and plug it into the original equation. This is your residual. Okay. So the original equation is du dt plus u. Lambda is 1. Okay. So wherever you have the 2 indicates it's a second degree polynomial. Okay. So you plug it in, and this is your residual. Okay. And there are 2 numbers that we need to find in such a way that this residual is minimized according to all the methods that we have seen before. Okay, so I'm not going to go through that part very in detail because we already seen that. So this is the residual equation, and what he does is in the first example, I think it is a subdomain method. Okay. This is a collocation method. Choose T1 equals 1/3, T2 equals 2/3, two equally spaced points in that interval 0 to 1. Okay. And so you put that into that residual equation, the values for T1 equals 1/3 and T2 equals 2/3, you get two algebraic equations. So this is with 1/3, this is with 2/3. You get two algebraic equations from that. Okay, that you should be able to, just an algebraic manipulation, you should be able to do that. So solve those two equations and you get a solution. Okay, and that solution is this, from collocation method. It's a global solution. The trial function is being quadratic, so you'll see only up to t square term. We have found the best value for these coefficients that appear here by collocating at those two equally spaced points. Okay. The next one I think is probably the subdomain method. You can see it here, delta T1. So I've divided the domain 0 to 1 into two equal intervals, 0 to half and half to 1. Here I need to spend some time to set the stage for the difference between subdomain method and the finite element method, because it looks like I'm dividing my domain into subdomain. So is it the same as the finite element method? The answer is no. The reason is when I'm doing this, I'm splitting my integration to each one of those subdomains, but the function itself is valid over the entire domain. The function is not limited to that subdomain. That's the main difference between finite element method and this method. Okay, so this function that you will get with a new coefficient will be valid over the entire range t equal to 0 to 1. Even though I need two conditions because I have two unknowns, and I take those two conditions as integral of the residual in the first half, 0 to half, and the integral from half to 1. So I get two equations. So I'm distinctly minimizing the residual in those two subdomains. Okay, but that is not finite element method, because the basis function is still spanning the entire domain. So here is the integral from 0 to half. This is actually done in very detail. So if you want to go through this later on, it will be very easy for you because he laid out all the intermediate steps. Okay, so plug in the residual expression that we have here, carry out the integration, substitute the limit 0 to half, and you will have to evaluate only quadratures, integral of t, integral of t square at most. Those are fairly easy to integrate, and then substitute the limit. Okay. But once again, you'll get two equations like that. This is from half to 1, and you get a second equation. These are 2 by 2 matrices. Now it's full because it's a global method. Okay. And you get a slightly different solution for these coefficients. Okay. And the third one is one where you use least squares. And this is where I think I had some confusion last time. In the least squares method, you are forming the square of the residual over the domain, and you are minimizing that by taking the derivative of that objective function with respect to the unknowns ai and setting that equal to 0. Okay? So r square becomes 2r dr dA. So this is treated as your weighting function. So if you choose your weighting function to be the derivative of the residual itself, then that becomes equivalent to minimizing this residual square, and that's the least squares method. Okay. Once again, it's a matter of taking you can take the derivative because you know the residual, plug it in here and carry out the integration. The steps are going to be a little bit tedious, but you can do that. Okay. All these essentially fall into this category. Okay. Method of weighted residuals, where the weighting function is different choices, delta function or subdomain, break it into two or three domains, and you're using essentially very small number of unknowns, 2 degrees of freedom, 2 unknowns. Okay. In COMSOL, you typically use 20,000 or 30,000. But the process is very similar to what's going to go on here. There is a graph here, that's what I wanted to show you. Now he's kind of recapping in the context of trying to generalize the 2 by 2 system to an n by n system where psi I are your basis functions and psi 0 refers to the boundary condition. In this particular case, the basis functions are these, and the way that you calculate for the Cullerton method, the weighting function is the basis function itself. We also saw that in the last class. So it's the same idea. And once again, you get two equations, okay, and you can solve them to get yet another approximation by the Cullerton method. And the figure that compares all these methods is the impressive one here. Okay, so this is the domain 0 to 1. Okay, 0 to 1, and what I'm plotting is the solution. The solution goes down as we saw, and here you have the exact solution and the solution with the collocation, subdomain, and Cullerton method. They've all done well, even though they have different coefficients. The condition that we imposed is different. In the collocation method, we impose the residual to be 0 only at 2 points. In the subdomain method, we minimize the error in 2 regions by dividing it into equal to a number of domains. So the coefficients A1 and A2 are slightly different in each case, but when you plot them and compare it against, you really don't see significant difference. Okay, you might begin to see something here with the subdomain method. But the question that we posed earlier is, how does the solution look when I take it and extend it beyond 1? Okay? Because I've minimized the error only in this region, but the solution is valid for all t going to infinity. We have the analytical solution. We know what it does. The analytical solution just continues to go down to 0 as t goes to infinity. Do these numerical solutions also do that? And that's given in the next figure. For 0 to 2. Okay, so we fit it only up to here. So from this point on, they are all extrapolations of the solution. And we'll find that the analytical solution goes like this, but all the numerical solutions begin to depart. Okay, so if you want to get a good solution over the domain 0 to 2, what do? You go back and change the integral limit from 0 to 1 to 0 to 2 and recompute your coefficients A1 and A2. Now we have a choice there. You can say, I'm going to use still only 2 degrees of freedom, and that means you're trying to get this to as good a possible solution with only 2 degrees of freedom. It's going to be a bit more challenging. So the error that you will sustain will be higher. But if you increase your degree of freedom to 3 or 4, chances are that you will get much closer agreement. Why is that? Because analytical solution is in infinite series. The more terms you take in that, the better accuracy that you get. So you need to mimic that in the same way. Another way of asking that question, which is what I think ties it to the finite element method, is instead of proposing a solution that is valid over increasingly larger and larger domain, can I keep the degree of freedom to only 2 per element and divide this into multiple elements? For example, I do one fitting, do the minimization. That is, I keep the solution that I got so far. Okay, but I resolve the problem by saying I'm going to construct a separate different function in this domain from 1 to 2. So my residual integration limits go from 1 to 2 instead of 0 to 1 or 0 to 2. But I'm going to use the same quadratic equation. But these are 2 different coefficients for this domain. So each domain I will have a local function. The coefficients of those local functions will change from point to point. Okay, that is the idea behind finite element method. Okay, so if you can do it for 2, then maybe you can do it for 4. If I do it for 4, I'm going to have 2 constants per segment. So I'm going to have 8 constants that I need to solve. I need to resolve this 4 times. Okay, but the more number of elements that I break that into, I'm going to get better and better accuracy. Okay, that's essentially what finite element does. Now the problems are, immediately you can say, well, I'm going to now track 8 coefficients. What is the difference? Why can't I go for one global polynomial with 8 coefficients, with a 7th order polynomial, instead of going for 4 elements, each one with 2, or 8 elements, each one with just 1, right? A linear approximation. Is there an advantage of one over the other? Okay, what do you think?
approximate each segment more linearly, or each segment is more correct than the global one would be overall. So your total error will be smaller.
Yeah, I guess for those in the PI, the question that we are discussing is it better to take a higher order polynomial that's global, or to take lower order polynomial in each sub-region, that is the driving force for the finite element. And Aaron's point of view is that you should take lower order elements, but more elements that will give you the greater accuracy. Right? That is generally true, and the other advantage that you have with breaking it into smaller elements is you can fit more complicated geometries. Now, for one-dimensional problem, it's not as significant, but if you have two-dimensional problems with weird geometries, you can break that into triangles and fit that much more easily than having a global function. Okay? So these are the reasons why finite element method have dominated. So if you have a global function, the structure of the function is somewhat determined by the function that you choose. So if there are sharp boundary layers and you have picked a function of sine, it doesn't have the boundary layer nature, then you're stuck. You need to take a lot of terms. And are you all familiar with Gibbs phenomenon? It sounds familiar. I had that in the notes in the last lecture, but somehow I skipped through that. And the Gibbs phenomenon is a good example. Okay, what it is if I have, I think the example that I had in the notes was, I have a straight line like this. The function is equal to x. And I want you to approximate that function using Fourier series. Right? Fourier series is a terrible approximation of that. Why? Because it goes up and down. And so you need to assemble these in such a way that they cancel. The ups and downs, when you add them up, they cancel it to give you this. And go back and see in the notes, and he has f approximated as a coefficient ai, for example, sine omega x. Okay. So what would happen if you take 2 terms, 3 terms, 4 terms? One term would be a terrible approximation because it will go something like this. Right? You cannot really fit that. But what he shows is as you take more and more terms, you can have wiggles like this. Right? But if you take really large number of terms, you can control these wiggles quite well, except at the end. These wiggles kind of will be pushed at the end, and there will be strong, higher amplitude wiggles at these parts. The same thing happens for control people. This is a very famous problem. If I have a step change, and I try to fit that function by a Fourier series, I will get the same problem. I can probably get this accurately fitted, but in here, I'll have wild fluctuations. The more terms that I take, in principle, I would say I should get a good approximation, better and better approximation. And you will find that this gets worse and worse. That's called the Gibbs phenomenon. So the point here I'm trying to make is that if you pick a global function, it may not represent the physics as well. If you have a boundary layer, you need to know, okay, is it Legendre function, is it Chebyshev polynomial, which one would have maybe Bessel function that will have a good boundary layer type of a character. If you pick that function, then you can probably do better than the finite element method. Okay? And this is why the so-called spectral methods are very popular and very accurate. And with about 128 terms in the Fourier series, you can really capture turbulent characteristics quite well. And the direct numerical simulation of turbulence has made advances using the so-called spectral methods. Okay? Those are global methods. And there you simplify the computational problem by saying I'm going to consider a cube, Navier-Stokes equation in the cube without any turbulence modeling, but I'm going to put a periodic solution in all 3 directions, spatial directions. But the modes are going to be going from 1 to maybe 128. Frequency is higher. So the more higher frequency you want to resolve, you take simply more terms from that. Okay? So that is the whole area of direct numerical simulation where spectral methods have been very successful. So you should not knock one term or the other, but they have their use. Spectral methods have their use, finite element methods have their use. And the advantage of the finite element method is you can adapt to the geometry, you can adapt to the solution. Okay, so if you have a sharp gradient somewhere here, and then the solution is like this, you will be able to get that by resolving this into finite elements to keep the error, which is what Aaron pointed out. Okay, so that's the kind of a reason and motivation. But the challenge is I need to keep track of more and more coefficients as I divide my domain. So can I kind of get rid of that? And that has been done by formulating the problem in such a way that you get rid of the coefficients and express the unknowns in terms of the nodal values. Okay, so either you take, so far in method of weighted residuals, we have an analytical representation, an approximate representation of a function which has coefficients. And we find the best value of these coefficients, put them back, and we have an analytical solution that we can evaluate at any point that we want. So in finite element method, just like in finite difference method, what we do is we get rid of these coefficients and express them in terms of the nodal values themselves. So we need to see how that is done. That's done in a very clever way, so that we still get the equations at the nodes only in terms of the nodal values. The same thing happens with finite volume method, which we'll see in the next class. Okay. So here is a different problem. Okay, it's a second order equation, a truly boundary value problem with the homogeneous boundary condition, but there is an inhomogeneous forcing term. Okay, so the solution is non-trivial, and we have a definition. Whenever you see this thing in parentheses, u comma v, we are talking about this definition of an inner product between those two functions. Okay, so b and w are two functions, and we will assign meaning to them. One of them would be the trial function, the other one would be the weighting function. Okay, so we are defining an inner product in this range 0 to 1 in this particular case in this symbol. So further down in the notes, whenever you see the things in parentheses, in your mind you should replace that with this integral. That's what that stands for. Okay. And finite element method, just like the method of weighted residuals, is an integral formulation. Okay. So one of the things that we need to understand is what is this weak formulation? What do they mean by that? You can see that he is a mathematician. It is the notes I picked up is from the mathematics department. Okay. So he defines a space. This used to terrify me. I'm not a mathematician, so whenever I read a paper with functional analysis context, I wouldn't understand anything. So I would go to a mathematics guy. Luckily, I had in my life two people who have helped me a lot in understanding the math behind these interesting ideas. Okay. One was a German professor, initially he passed away, but I spent 1 year with him in Germany on a sabbatical. That's where I learned all these Auckland continuation and bifurcation methods. These are all published in applied math journals in functional theoretic context. But he kind of peeled those layers for me and explained how I would actually implement it. Right? And same thing for finite element method. I have Peter Menev, who is in the University of Alberta, who has helped me understand all these ideas. But it's not. I mean, what do they mean? Omega is a space of functions with certain properties. Okay. One is that property u is continuous in the domain 0 to 1. And du dx is piecewise continuous and bounded. So these are functions that don't have singularities, they don't blow up. And piecewise continuous means in each section it is continuous. But at the edge you could have a discontinuity. So if I'm taking this domain 0 to 1, and in this particular case I'm plotting u as the solution, my solution could be like this. Right? That's what piecewise continuous essentially means. So you could have discontinuities at the edges. Okay. So we need a functional. So what does this mean? This is the process that I went through with my math colleagues. When you read something like this, you should be able to decipher what the symbol is. They already defined what the parenthesis means. Right? The parenthesis is the integral. So this would actually mean this is equal to 1/2 integral of du dx multiplied by du dx multiplied by integral of f u dx. And that's what, now where does this come from? It is related to the residual, and that's what we're going to see. We already seen what a residual is, we know how to construct the residual, but how is it related to this particular formulation? So we're just saying we also need a functional, What is a functional? Have you heard that term before? Functional is a function of a function. Okay. So f is a function that is defined as on the right hand side, but f is a function of u, and u itself is a function of x. So a function of a function is what you call as a functional. Oh, so they have it here, which is the shorthand notation for that integral representation. Okay? And here u prime is du dx. Okay? So they're saying that in the finite element approximation, there are two alternate ways of looking at it. And this is historically how finite element method evolved from civil engineering, from structural engineering, structural mechanics, solid mechanics, etc. One, what they call the variational problem, okay, and the other one is they call the minimization problem, okay. And the problem is find the solution u from the space that I have defined. What is that space? Space of continuous functions with piecewise linear derivatives, right? And in such that this condition is satisfied. U prime, v prime, meaning keep this integral in mind, okay? So it is the integral of du dx dv dx minus integral of f v dx, okay, is equal to 0, okay? We need to find the function that satisfies this equation, or we need to find that function u such that the minimization, that is the functional, is minimized. So when we say the functional is minimized, one of the ideas here is that you are expressing the functional as some representation of the energy of the system. And so you know that the energy should go to the minimum, right, for an equilibrium point, for a stable point. So you try to minimize it so that you try to minimize this functional f. That is, think of it like this. As an engineer, I have different functions in my toolbox, and I take each one of these functions and plug it into the functional and evaluate the functional. I get a number. Because it's all integral. I can do that, I will get a number. I keep that, and then I take the next function, and I put it through this machinery, and I get a different number. So the next function gives me a number that is lower than the first one. I'm going to keep the next one. If not, I'm going to throw that out. Okay? So I'm just comparing which function gives me the minimum for that energy. So the interpretation is that this represents some sort of an energy of the system. That functional represents the energy of the system. And here he actually gives you an interpretation. The energy of the system can be thought of, this is for a simple harmonic oscillator or spring, an undamped, I guess, a spring system. So the total energy is consisting of T plus V. T is given by this. So we are actually having a physical example in your mind, okay? And V is given by this. What could T represent? If x represents the position, dx dt represents the velocity. So that represents the kinetic energy, mass times v squared, mv squared, right? So this is the kinetic energy, and this represents the potential energy of the spring. Okay, that is, if you expand the spring, that is x changes, you are applying a certain force, right? So that energy is stored in the spring. The moment you release it, it's going to go back to its original position. So K would be some kind of a spring constant, and V is the potential energy of the spring. So there are two ways. There is an excellent book by Richard Feynman, of course, called The Character of Physical Law. Has anybody read that? It's a very small book. I read that when I was a graduate student a long time ago. I haven't read that recently. It was based on a lecture, I think, that he gave at Cornell or something. These days you should be able to download it because it's probably out of copyright and all that. It's a good book. You should read that because he talks about these two ways of looking at any universal phenomena, any phenomena that we look at. One is in terms of the energy perspective, the other one is in terms of the force perspective. Right? So we can write the equations either in terms of equations of motion and force or in terms of the energy, and you can derive one from the other. What is the relationship between them? We in fact saw this in the transport phenomena course when we looked at the momentum equation and derived the Bernoulli equation. You remember Bernoulli equation and energy equation, mechanical energy equation. How did we do that? Those are the kinds of questions. You don't have to prove anything, but it's a concept. It's a very important concept, right? We take the force multiplied by distance is work. So distance over time, force multiplied by velocity is rate of work done. Okay, that's basically how. So we took the momentum equation, dotted with v. Momentum equation is a vector. You dot it with v, so you get a scalar, and that is your Bernoulli equation. If you ignore which one? Pardon me? The frictional force. Very good. You get a point in an exam. So the frictional force, the viscous forces, right? So you start with your Euler equation, you dot it with V, and you get your Bernoulli equation. What you should at least remember is from your undergraduate fluid mechanics course, the Bernoulli equation doesn't have friction in it. You throw it as a fixing afterwards, right? So that's a relationship between the force representation of a model and the energy representation of a model. And that's essentially he's going to go through here. Okay? So this is the energy representation. So I have a spring system, and there is a kinetic energy and the potential energy. And that's a total sum of energies. Okay? So you just substitute for dx dt is in terms of u bar, and that's x squared. Okay? So that is your total energy system that you want to minimize. Okay? So how do you minimize a function? Take its derivative and set it equal to 0. How do you minimize a functional? It's the same idea, right? Take its derivative, but how do you take the derivative with respect to a function? That is the thing that you need to worry about, right? Because you're taking the derivative of a function with respect to a function, right? And that's what this is about. Okay, so that E is thought of as a function of x and x prime. Okay, that actually, yeah, u dot stands for, u dot is not the derivative, u dot stands for the derivative of dx dt. Okay, so you treat this function E as a function of x and x prime, function and its derivative, x and the velocity. Okay, so this function E can change if you change the position slightly. That is, if you pull the spring, you're going to change its energy. You're going to store maybe more potential energy, right? Or if you give it a kick, a velocity, change its velocity, you're changing its kinetic energy. So the total energy can change either when the potential energy is changed or when the kinetic energy is changed. Okay? So it's essentially chain rule applied to function of a function and set that equal to 0. Okay? Now it looks like we have come far away from method of weighted residuals. Hopefully it will all come together later on. You will see the relationship that in some cases, when you have non-dissipative systems, conservative systems, where there is no dissipation mechanism, Euler equation being one example, but in solid mechanics there are the Hamiltonians. So these are all representations of some form of an energy, and the minimization of the energy becomes a natural way to express, and your finite element method falls out of that, minimization of the energy. In those cases where it is not possible, we start with your equation of motion, and we form what we call the weak form of the equation, and we again convert it into an integral representation. Okay? So that's where these ideas converge. So in those cases where you have a natural representation of a total energy and you are minimizing that, and I'm telling you here, for example, this equation comes from taking the derivative of this and plugging it in there. Do you see the connection? Can you see how I can get this equation from here using this? Go to that, take the derivative of that. Now m is constant, k is constant. That, okay? So I'm taking the derivative of this with respect to x in the first case, right? When I take the derivative with respect to x, what happens? This doesn't contain x. So I will get 2x dx dt, right? So the 2 and the half cancels out, and I will simply get kx multiplied by dx dt. It's there, okay? And then I take the next term. I'm taking the derivative with respect to x dot. X dot is what they call, I think that should have been an x dot there, right? So it is u squared, the derivative of that with respect to u. U is the same as x dot, okay? So you'll get 2u du dt, right? Yeah, du dt. So that is m. So the m cancels out, but du dt is the same as d square x dt square, because u is dx dt, right? So if I didn't know anything about the energy, I could write this equation by making a momentum balance, right? So this is Newton's law. Mass times the acceleration is equal to sum of the external forces. And the external force here is only the spring, right? So without knowing anything about the energy, I could write down from a force balance point of view. And this is the idea that is explored very nicely in the book by Richard Feynman, okay? Or I could start from this and derive that equation. Then the question that you have to ask is, can I start from this and go back? If I knew momentum equation, how would I get the energy equation from that? That's what I talked about in the Bernoulli equation. So take the momentum equation, dot it with v dot, and you'll get your energy equation. Okay? We're all talking about this in one dimension, but you can extend that to 3 dimensions also. So minimizing that is equivalent to solving this differential equation. So in the area of calculus of variations, you will call this as the Euler-Lagrange equation. Okay? That's your functional that you're trying to minimize. When you impose that minimization condition on that, you'll get your Euler-Lagrange equation. And there are two versions, two views of solving the same problem. You can choose to solve this problem, you can choose to solve this problem, you'll get the same solution from either one. For non-dissipative systems. If you have a dissipative mechanism, then this is not exactly possible because there is an irreversibility, and so you need to, that's when you use the method of weighted residual framework comes in handy. There also you have an integral formulation, and here also you have an integral formulation. Any questions? Yeah, here he basically shows what we did for time. Variational formulation is actually equivalent to the original differential equation. That's what we talked about. Okay? So if you are given the variational formulation as the energy, the variation of the energy, minimization of the variation of the energy, it gives you a differential equation, okay? Which is the force. So the gradient of the potential is the force, right? So the force dotted with the velocity vector is your potential, right? So you can go back and forth. So it starts with the same equation. Remember, whenever you see this, you need to put in your mind the integral. Okay. So this is the integral of d square u dx squared, the second derivative, multiplied by v, which could be a test function or a weighting function in our terminology of method of weighted integrals, is equal to minus f integral minus f v dx. Okay, so let me ask you, I guess he says it, but can you see, okay, the left hand side by parts and use the fact that these are the boundary conditions. So what has he done here in this line? If you develop that ability to interpret, then you can read any paper and try to understand that. Okay, so you need to be able to go through the logic and see, okay, this is what is happening here. So this term is the same as the first part of this term. Oops. Right? And do you know integration by parts, right? What does integration by parts do? Integral of uv dx, when you have two functions, it is integral of
UV minus UV.
u dv. There's another form that you have.
Is equal to
uv minus integral of v
ddu.
ddu. Right, you got it, right? So that idea is what is imposed here. And one of them is evaluated at the boundaries, the other one remains as an integral, right? So this is the part that remains as the integral. Okay, these are the values at the boundary. Okay, and what has happened by doing that integration by part? The order of differentiation, the highest order of differentiation, which was second order, has been reduced to first order. So the test functions that you are considering must only be differentiable once instead of being differentiable twice. Okay? And that is what is called a weak formulation. You don't have to have a function that satisfies your differential equation and have the requirement of differentiability twice, because the highest derivative that you are ever going to take in this formulation is only the first derivative. But these are the same equations. All I've done is it's a rigorous transfer from here to here. I'm using integration by parts. Okay, so this equation is no different from the previous one. That is a modified equation. Remember, again, you need to put the integral in there. But that integral, this is what we started off when he gave you the function f. He just wrote it in this form. But where does it come from? It comes from this idea of transferring a second derivative in the integral formulation using integration by parts into the first derivative. So this is typically what is called a weak variational formulation. Okay? Still a variational formulation, but it is called a weak form. The reason is that it doesn't have to have a differentiability requirement that are stronger. It can be weaker, just first order derivative. The other point that you need to note here is the boundary conditions. When we saw the finite difference method, we said that Dirichlet boundary conditions are natural for finite difference method. Why? Because we have unknowns at the nodes. So if you have at the nodal value at the end boundaries, if you know the value, just substitute that, right? So it's very easy. But if you have a derivative boundary condition for finite difference method, you need to treat the derivative with a backward difference or a forward difference and redo the problem. In finite element context, what you will find is, if you know the derivative boundary condition, it's very easy to implement them because the derivatives appear here. So the derivative conditions or the Neumann conditions are called the natural conditions. So in your discretization process, you don't even need to worry about this. They are automatically taken care of if they are equal to 0. Okay, if they are non-zero, then you need to put the value. But if they are equal to 0, they are automatically taken care of. Okay? So that's why you hear about this thing that in the finite element context, the Neumann conditions are natural. They fall out of this integration by part procedure. So this is true for just one dimension, or also for 2 dimension or 3 dimension, except these boundaries will be on a surface or a curve for 2 dimension on a surface for 3 dimension. Any questions? So example of a Cullerton formulation for Poisson equation. Just a big name. This is essentially a second order Poisson equation in 1 dimension. Okay, if it is in 2 dimension, you have a 2-dimensional elliptic operator with the forcing function on the right hand side. The forcing function is 0, then you call it a Laplace equation. But for 1 dimension, it is essentially a second order ordinary differential equation, the same one that we have been talking about. But now we are going to, we've been talking about abstract ideas on what is the equivalence between a differential equation form and the integral form, and what is a weak variational form, etc. Now we are going to actually talk about implementing our ideas into solving this problem. The Cullerton formulation. What is the Cullerton formulation? This is the key new idea in finite element method. If you understand that graph, then the rest is fairly easy. What does that graph tell you? It tells you that I'm going to construct my basis function with certain properties. Okay, I'm going to consider, for example, a linear basis function. I'm going to define that function such that it is 0 at x0, 0 at x2, 1 at x1, and 0 everywhere else. That will be my first basis function. Then I'm going to construct basis functions like that for phi 2 and phi 3, etc. Any number of basis functions that I need. The beauty of this is it's going to allow us to satisfy, we don't need to compute coefficients and put them back to calculate the actual solutions.
You said it's 0 at x0, 0 at x2, 0 and 0 everywhere in between except...
No, it's 0 everywhere else.
Oh, outside.
But so in this region, it is given by that equation. Okay, but at x1, it will have a value of 1. So it is normalized. Okay, so it starts at 0. This straight line actually goes like that, and this straight line will go like that, right? But what we are saying is, I'm truncating it. Okay, so outside of that, whatever the function does, I'm not interested in that. That phi 1 is going to be defined only over that local support. That's what we call the local support. Right? The function is defined only over a local region. So what happens far away doesn't influence this. Okay? If you understand this idea, then it's all expansion of this to higher degree polynomial. Instead of a straight line, you can put a quadratic with the same concept, a cubic with the same concept, or you can do it in 2 dimensions or 3 dimensions. So that there's a lot of bookkeeping is involved immediately. So when you're implementing a program, it will be a lot of work. And that's where if somebody gives you a course on finite element method, they're going to take you through all these steps. Okay, let's do it for 1D, let's do it for 2D, let's do it for 3D, time dependent. So by the end of the course, you'll have a finite element solver in your hand for solving any partial differential equations. But we are exploring only the basic ideas. Okay, so that is the key idea of representing basis functions with a local support. Okay, so with that kind of a function, this condition will automatically be satisfied. Okay, this is the problem that we are looking at, where we have the second order equation with homogeneous Dirichlet boundary condition on both sides. So I'm going to divide my domain just like it did in finite difference method, except I don't have to require that they are all equally spaced. Okay, so the only condition is that they are ordered. So x0 is less than x1, x1 is less than x2, etc. And I start from 0 and end at 1. Okay, so I've built myself the ability to have flexible grid, non-uniform grid. The same thing happens when you go to 2 dimensions. You can put triangles, you can put quadrilaterals, you can put any other type of domain on which, and here the domain is just this. Okay, just a line element. But in 2 spatial dimensions, you'll have an area which can be filled with typically a triangle or quadrilateral, etc. And you need to construct a function. So in this case, we are constructing a function that is linear. We can construct a linear function in 2 dimensions. We can construct a bilinear function in 2 dimensions. What is a bilinear function? How would a function? This function is going to look like something like a plus bx. So, a plus bx is going to be my linear function. I need to fix a and b in each domain. Okay, and I've solved that instead of finding what a and b is after plugging it into the residual equation. I'm already fixing what a and b is going to be, but I make my unknowns as the values of u at these points. And that problem is solved very elegantly in this formulation. But if I'm going to go in 2 dimensions, suppose I have a triangle, okay, x and y. I'm just giving you a glimpse of how you would generalize this idea. Okay, so if I have a triangle like this, so if I take one of these triangles and I need to write a basis function, how would it look like? It might look like a plus bx plus cy. So now I have 3 coefficients, I have 3 points. I can do something with it to evaluate what those 3 points are and express them in terms of the nodal values. But if I take a quadrilateral, then I have 4 points, right? So I might say, well, I can add dxy. That would be called a bilinear kind of a fitting. You can then have quadratic and higher order as well. So any questions on this one? Let's see what the consequence of this by proposing a basis function like that. So this is the actual definition for that phi j. Phi j's are my basis functions. I'm going to define n of them, phi 1, phi 2, phi 3, etc. And they're going to have this definition. 1 over delta x multiplied by x minus xj minus 1. If x lies between that, j minus 1 to j. Okay? But if x lies between j to j plus 1, it is given by this. If x lies anywhere outside of this, it is 0, which is what I conceptually laid out and showed you pictorially, but now I'm mathematically writing this. And you can see that x has a positive slope in the first one and a negative slope in the other one. So this is these 2 straight lines. Okay? So if this lies between xj minus 1 and xj, it is the first part, the positive one. Okay? And if it lies from xj to xj plus 1, it is this part that is defined by this equation. That is my basis function. And if you evaluate it, for example, when you put x equal to xj minus 1, what happens? 0, right? When you put x equal to xj plus 1, 0. When you put x equal to xj, it's xj plus 1 minus xj divided by that delta x. So it's 1, right? So it has all the properties that we needed. 0 at both ends of the element and 1 at the center of that basis set. So that's what is kind of indicated here. Okay. And the beauty is, how do I construct my solution? Remember, I want to construct the solution u in terms of some unknowns multiplied by basis function. Right? So we have seen previously these basis functions coming from 1x, x squared, or sine x, sine 2x, sine 3x, etc. But now we have a new basis function which is defined locally. So if I write my solution in this form, if you understand that, the rest is exactly what we have done before. Okay. So what does this say? It says uj and uj plus 1 are the unknowns that I want to find. Okay. So those are equivalent to my coefficient. These are the unknowns. These are equivalent to the coefficients. The phi j's are all known, right? I can put in a value. For example, if I put xj here, what happens? In this is what I'm saying is this is my solution in that support, in that region. Okay. So if I put x equal to xj, this is going to be 0. That's going to be 0. I'll get uj. Okay. If I put in this expression xj plus 1, then I will get xj plus 1 minus xj divided by xj plus 1 minus xj, which is 1. 1 minus 1 is 0. So that will now be the surviving one, xj, uj plus 1. So I've expressed my basis, my trial solution in terms of the unknowns at the nodal points. Okay, directly. I don't have to calculate coefficients. When I solve this problem, I will get uj and uj plus 1, uj plus 2, uj plus 3, etc. I'll get a set of linear algebraic equations, a matrix, with u1, u2, u3, un being the unknowns. Okay? But I still need to evaluate the basis functions. I need to satisfy, I need to plug this proposed solution into my differential equation to form the residual, and I minimize the residual. Those processes are through the Cullerton process. Okay? So that means I pick my test function to be the same as the basis function. Okay? Do you understand the difference between the test function and the basis function? What is it? The basis function is one that you pick to represent your solution. The test function is your weighting function. Right? So you choose that to be the same as the basis function, the Cullerton method. So this is a graphical way of representing how the solution might look like if you're using the linear basis set. Okay? The solution is not going to be a smooth curve. The solution is going to be something like this. It's linear in each domain. So you could have a discontinuity in the derivative. Okay? That is, the derivative calculated from this and the derivative calculated from that can be different at those points, at the nodal points. And that's what is indicating here. Okay? So if you calculate the derivative of d phi dx, you have defined phi 1, phi 2, phi 3. If you go and calculate the derivative, you will find the derivative is either positive or negatives like that, and you have discontinuities when you're plotting the derivative against x. Okay? And this is, in fact, the derivative value that you will find. Because it's a linear function, so when you take the derivative of the linear function, you're going to get 1 basically, with the coefficient, and the coefficient that appears as 1 over delta x. So the derivatives will have that discontinuity. So here, actually, it gives you what the derivatives are, okay, for each one of those domains. Simply taking that function that we defined, take the derivative with respect to x, and that's what you get, and that's a graphical representation of that. Okay. So the solution is represented then in an approximate way using that alpha I times phi I. Now what is alpha I? Those are the coefficients in the proposed solution, but in our case, because we have defined phi I in a specific way, alpha I would be the same as nodal values of the unknown solution, UIs. Okay. This part should be familiar. What are we doing here? We are taking the proposed solution, plugging it into the differential equation, okay, and to form the residual. So that is the residual. And the summation, of course, is there. It has to be carried out. And alpha I are the unknowns at the nodal point. So we need to take the derivative of the proposed function. Now we have a problem. Proposed function is linear. So if I take the second derivative, what is it going to be? 0, right? So this is where we go into the weak variation formulation, do the integration by parts. Then all I need is the first derivative. Okay? And so that allows me to march ahead. And the other part that I should point out is the residual is multiplied by the basis function, test function. This is what you would call the test function, the weight function, right? And that is the same as the basis function in the Cullerton formulation. That's why this is called the Cullerton finite element method. Okay? So after doing that, you do the integration by parts, same as we did before. So reduce the second derivative to the product of the first derivatives that you see here. Okay, which you can take. And so you need to evaluate this inner product, if you like, between the first derivative of Phi, first derivative of Pj. Okay? And those are the ones that are going to give you the coefficients of the matrix. Okay? So the alpha i's in the solution, remember, U is written as summation of alpha I phi I. Okay? So when you plug it into the differential equation, you get the residual. You form the weighted residual using the test function as the basis function, and you do the integration by parts to reduce the second order derivative to a first order derivative, and you will have to evaluate this integrals. But these can be done once and for all. Why? Because my basis function is independent of the problem that I'm solving. Okay? I've expressed the solution in terms of the solutions at the nodal points. So these are just known functions. This is what makes possible building general purpose solvers. Because a lot of the tedious work of assembling the matrix, I have to do it only once. I have to figure out algorithmically how to arrange these calculations and assemble the matrix. Okay? And then I have to solve the linear system for alpha I. Alpha I is the same as Ui at the nodal points. Okay? So taking this derivative of the function, plugging it and carrying out the integral can all be done once and for all. So here he has phi j minus 1 or phi j minus 1 phi j. They are the same, and that simply reduces to this number. That I know, because I know where the coordinate positions are. So I can calculate what the delta xj. Okay? And so these are the coefficients, and almost at the end of, you need to do the same thing on the right hand side, of course. Okay? This you need to do problem specifically. Why? Because f comes from the description of the problem. Right? So you need to do that for each problem to construct your right hand side. And once you have done that, you assemble the matrix. And these are your unknowns, u1, u2, un. This is the forcing function that comes from here. Okay? And this is your matrix that comes from the inner product of phi I with respect to phi j. Phi I prime, phi j prime. So if you have a second derivative, this will come. If you have a third derivative, you'll have a corresponding terms that you need to worry about. What does that look like? After all this work, it's a tridiagonal matrix. This is exactly what you would have obtained if you had done central difference approximation, which I could do in one line, and I understand it completely. Right? Why did this happen? Because he made one key assumption, and that is points are spaced uniformly. Okay? So the real power is all these coefficients will be different if I distribute the nodal points differently. So there is a powerful thing that we can get out of this, all this work, but always we have to check that in the limit, does it, if I make a uniform grid space assumption, do I get back? Does it look like what I've known before? And I think that comes out beautifully in this particular example. Okay? I think we are out of time. There is another example. I think maybe you should. This is the same example instead of f. F is given as 1. Okay, and he takes you through a repetition one more time to get the solution. And that is a very good book for finite element method. I learned quite a lot from that. It's called the intermediate finite element method. It's not very elementary, it's not very advanced. He goes through in detail how to assemble these matrices, and he does it in 1 dimension, then 2 dimensions, 3 dimensions, linear or non-linear. So if you really want to become an expert, I think it's not a difficult book to read. For engineers with basic calculus background, you should be able to read that one. So in the next class, we'll start looking at the finite volume method, and we'll move on from there. I hope you get some idea of, I'm trying to just remove the mystery of what finite element method is. Okay? If I've done that, I think we have achieved our purpose.